So today we're going to talk about runoff modeling in GoldSim. So why do we want to include the runoff component in a GoldSim model? It's really important to ask this question before you design your model, because it could be that you don't need to include it in the model. It could be that obviously there are many existing tools out there that can do runoff modeling, including continuous runoff modeling, that are perfectly suitable and work well for that. And it could be that running the model there one time, then importing the results, the runoff results from that model into GoldSim could be the best option in your case. So something to think about. But why would we want to include it in GoldSim? I've listed here just a couple of reasons. First of all, that maybe you want to include uncertainty in a Monte Carlo simulation, which GoldSim is very good at. Another possibility might be that you have feedback from your main GoldSim model back into the runoff parameters of your catchment, or of something that changes the way that runoff is calculated. And those first two reasons might be a really good reason to incorporate the runoff modeling in GoldSim. It also might be that you want kind of an all-in-one model where perhaps it's just more convenient to include the input interface to your runoff model with the interface of everything else in your model, just to make it easy for your end user to have everything in one place. But I would say, at least my opinion is, that would be a lesser reason, not as important reason to include it in your model. And perhaps there are other reasons out there. I'm going to talk about A WBM and HSPF today. These are continuous simulation runoff models, and pretty well, A WBM anyway is very popular in the GoldSim community, and that's why I wanted to bring it up. HSPF has a lot of potential. We have not built the entire HSPF model in GoldSim. There's only a portion of it, but what is there is pretty solid. So I wanted to talk about that as well. Anyway, AWBM is it's used heavily for arid regions, and works well for that, but it could be applied in other areas as well. That's just where it's been used a lot that I'm aware of. It is one of our most downloaded models from our library, and it's also quite simple to use. There are relatively few inputs for what it's doing, and so that's probably one of the reasons why it's so popular. But as you'll see in this presentation, it can be calibrated to observe runoff pretty well, and so I think it is a pretty good model to use in some cases, and it is all in GoldSim, so that's nice. And it does work well for continuous simulation. So the strengths of HSPF is that it is well tested. It's used a lot in research, so it has a lot behind it. It is very flexible and can be adapted to a lot of different conditions, and has been. And again, it's continuous simulation, so that's good for GoldSim type modeling. It is comprehensive in its representation of the runoff and stream processes, and also for pollutant sources and loading, but the part that is included in GoldSim right now only includes the runoff for pervious catchment. And while the whole reason behind HSPF is for pollutant loading, water quality, we have not built that portion into GoldSim at this time, although any of you could do it if you wanted to. So a little bit of background behind HSPF in case you're not sure or haven't heard about it, is that it includes quite a bit in there. So at the catchment level, you can look at snowmelt, sediment transport, nitrogen, all kinds of things. And there's also the impervious land segment portion. So what I just showed you, the box up here is for the pervious land segment. There's also impervious land segment for urban areas. And then there's also the reaches as well that you can simulate a lot of different type of functions in there. Now again, what we've put into GoldSim is only the runoff portion for a pervious land segment. So a portion of this box up here is all that's in there right now. And that portion that I just mentioned, runoff from a pervious land segment, is represented in this schematic. So this is what is built into GoldSim to produce surface runoff, interflow, outflow, and that is cut off on the side here, but that's groundwater outflow. So it accounts for all of those flows. Okay, so let's look at applications now. First of all, what I want to talk about is kind of what do we compare against? So how do we validate the model, the GoldSim model part, and what do we need something to compare it to, right? So what I did is I installed HEC-HMS, the latest version, and with HEC-HMS comes a couple of example models. In this case, there's this one called the Tifton model. It's very simple. It has 2 nodes in it, and one of those nodes is a catchment type node here. It's called a subbasin, actually, in HEC-HMS. But all it does is it uses some functions in here, built-in functions to calculate runoff, and then you can compare the runoff to observed discharge flows from this catchment. So all I did was generate results from this model. You just come up here in HEC-HMS and do a run. So there's a run, and then you can look at results. Just right-click, view results, graph, for example. And here is a plot down here at the bottom, the flow. I just took the results from this, the inputs and the outputs. Actually, I put all of the inputs into an Excel spreadsheet so that I could make sure that I have all those organized and accounted for, and then I was able to put those inputs into GoldSim, not using the same functions, but actually using A WBM and HSPF. I just wanted something to compare results to is all, and also have some observed flows time series to do a calibration. Okay, so this catchment, given some rainfall values and also some properties of the catchment itself, for example, here's the area over here on the left, the area of the catchment. There's some information about the canopy, the surface here. And by the way, if you go back to the subbasin, you'll see that the methods that are being used here for losses and so forth are specified there. And based on those methods that you choose, then you enter the inputs for those methods. And so you can see here are all the methods. So for the loss, there are all of these, and so forth. Okay, so given that, then we come over here to A WBM in GoldSim. So let me close this down for a bit and come over to GoldSim. Now, what you're going to see a little bit of today is our upcoming release of GoldSim. I started building this in our alpha or beta build of GoldSim, and so it's yet to be released. It's not something you have yet available, but soon. So it'll give you an idea of what GoldSim is going to look like very soon. Mostly what you'll see is that the graphical interface has changed. All of our icons have been updated as well. So anyway, this is the AWBM model. You'll see exactly the same thing if you download it from our website, except you'll just be in the older, well, in your current version of GoldSim. So the icons will look different. But anyway, what I did is I took the same exact precipitation time series from the HEC-HMS model. This is the same exact evaporation table. This is just a table of 12 values for the months And then I took the HEC-HMS runoff time series from, here's the time series right here. I took that from the HEC-HMS model as well. I just want to check to see if there are any questions at this point. And it looks like there are not. Okay. So I have mentioned in past webinars how you can use optimization to do a calibration of a model, and that is where I was heading when I was preparing for this webinar. But I have to say that it actually turned out in this particular case to be easier to do manual adjustments of inputs instead of the optimization. So what do I mean by optimization? Well, let me just start a new version of this model and give you a taste of what I'm talking about with optimization to do a calibration. So I'm going to open a new model. This is it's the same model, but I just didn't want to mess with the one I had open. Okay, so this is a AWBM model, and I'm just going to do a save as here, and I'll call this optimize calibrate. Okay, so this is just looking at a single catchment, with the same properties essentially of the catchment in the HEC-HMS model. And in the AWBM model, if I open the AWBM calculations, go in here, this is the AWBM model. There's a schematic of the logic right here in this container, and it looks like this. So this is how it works. The rainfall time series comes in and drops into these 3 different surface stores that all have varying depths, and when they fill up, they overflow and they come into 2 pools or buckets. One is surface runoff, one is base flow store. And then there's a recession constant that's used that determines the runoff from both the base flow and the surface store. Typically your surface store would be very peaky, very high spikes that would discharge quickly, and then your base flow would be more gradual and attenuated much more. And the combination of those two are just added up together and you get your total runoff. So that's how this thing works. And you can download this from our website. Let me open our website real quick. So go to our website and go to library here, and then go, well, you could just search. I suppose you could just search right here in the search bar, AWBM, and there it is. And you can read about it and then download the model as well, and you'll get the same thing. Okay, so it's currently built for a single catchment. Now, you could just replicate this thing multiple times for each catchment in your entire watershed if you wanted to. Or you could do this as a vector. So all the calculations in here would be vector calculations, and we've already done that as well. So if you go back here, you'll see that in my search in our library at the bottom, Australian water balance model for multiple catchments. If you click on that, you'll see that it's the same thing, but it's made for multiple catchments. Yeah. So I think what we did in there is we just vectorized all the calculations. So it would probably look exactly like this, except everything is just vectorized. So for all the catchments. So you'd have to just, instead of entering, for example, one number for your C1 surface store, you would be entering the number, a table of numbers for all of the different catchments. Okay, so these are the calculations for it, and there are some inputs here, and I'm gonna just change these a bit. I'm just making up some numbers, and typically, and by the way, C1, C2, C3, those correspond to the surface store catchments in the AWBM functionality here, and they should be getting, typically they'd be getting larger as you go from C1, C2, C3, C3 being the largest. And so let me just do that, just make up some numbers. The other variables in this model that are important are this BFI value. This is really called base flow index, and it determines how much of the surface store runoff will go to base flow store and how much will go to surface store. So it's just a fraction. So if you put in a larger number, then more will go to base flow. A smaller number means more goes to surface. And then you have the recession constants here. I'll just make some up. I'm just putting random numbers in here because I want to show you what optimization does to do the calibration. Okay, so I have a calibration box here that I've added to this model to calibrate to the observed discharge. So if I run this model, then we can go to look at the runoff comparisons chart. Well, let me first show you just rainfall runoff. So rainfall runoff looks like this. So the blue up at the top is the rainfall with Y2 axis, upside down. Then the runoff here is shown in red, and then it's overlaid on top of the observed discharge. So you can see it's decent, it's okay. But what I'd like to do is do an optimization to try to better match the observed. So how do we do that? Well, I've assumed that I could use an R-squared as a best fit against all of the points along the time series. So I do that with this calculation here, and that's represented here in these integrator elements. So I calculate R-squared here. I tried, in addition to R-squared, to look at the peak flow, because in addition to trying to get a good match of all the points, it might be even more important to also try to have a peak flow that matches the peak in the gauged time series. So let's say, for example, this peak right here, maybe that's the most important, is that you get a peak that matches. So in addition to matching all the points, I said, okay, well, what's the difference between my calculated peak and the gauged peak, and then factor that into what I'm calling a calibration score. So, I mean, I ended up turning that off. Multiply it by 0 there. I turned that off because I was finding it wasn't really helping that much. So anyway, let's go to calibration now. So in this model, what we have are essentially 1, 2, 3 inputs plus our surface store depths, these 3 right here. So that's 6 inputs that we can adjust in our model to try to get a better calibration. So in GoldSim, you come up here to run and then optimization. Then what I'm going to do is I have an objective function. In my case, I want to maximize my objective function, which is my R-squared plus this this peak difference factor score. I call it my calibration score, but really it's just my R-squared. I'm trying to maximize R-squared. Then I have my inputs, 6 inputs, plus I also looked at my pan coefficient because I wasn't quite sure about that. I should probably just take that out. Let's see, is that still 1.7? Yeah, it's 0.7 in the HEC-HMS model, but I was trying to make some adjustments there as well to see, because that's kind of an uncertain factor anyway. So I included that in the optimization. Well, how did I know to include that? Well, we should really do a sensitivity analysis before we do an optimization, because why put optimization variables in there if they don't make any difference to your output, right? So probably a better idea would be first to start with sensitivity analysis, which can be done in GoldSim. Go up here to sensitivity analysis. I have all of those 6 factors in there, and I could add the pan coefficient here as well. So let me just do that. So in sensitivity analysis, you just need to put a range of possible values. I'll say 0.5 to, let's say 0.9. Okay, and then you can do what's called a tornado chart. And this gives you a good representation of kind of the range of all of your inputs and how that affects your output. So what you can see here is that the model is most sensitive to the KB. The KB is the recession constant for the base flow store. BFI, that's that split factor that splits between base flow and surface flows. And then the remaining 5 are the model is less sensitive to those. And it could be that you say, well, C3, I mean, that's not really making a big difference. I should probably just not include that. But let's say I included some others. There are other inputs in here, and I could have included all of them, and you might see that they diminish as it goes down. But the tornado chart is really useful for showing you how sensitive your model is to all of these different factors, and that would play into deciding whether you include them in the optimization. I mean, you don't want to include 50 inputs, 50 optimization variables in your model. It'd be very difficult to complete the optimization and get a good answer from that kind of a run. So it'd be good to weed out the ones that the model's not sensitive to first. You can also look at individual plots on the sensitivity, like this one here. Notice it's doing a run every time I click on one of these output charts, because essentially what GoldSim's doing is it's just doing an individual run with the different values that I've specified in the range of inputs for C2. So in this case, we see that for varying values of C2 between 0 and 600 millimeters, we get an R squared, as you see over here on the y-axis. This would also help us determine the range of optimization variable for C2. So for the optimization, we'd probably want to stay in the range where the R squared is up higher. Could be. Now, there's also the case of the combination of inputs that would create an even higher R squared. So we need to be aware of that as well. But you might get some cases, let's see if we find one, where it flatlines. Okay, we don't, not here. Look for a couple more here. In some cases, you get a plot where the line is flat, and that would be a case. Maybe here, for example, in the low range of KB, it could be that that it doesn't make a big difference to the model in this lower range here. But it also might be that you want to stay away from the values that where the result is dropping down significantly. Okay, so studying the sensitivity analysis results here can help you a lot before you enter them into the optimization, because in the optimization, it makes a big difference if you start adding a lot of optimization variables and also a wide range on all of your optimization variables. It'll take a lot longer for it to find a good solution and may not find the solution at all unless you do multiple runs, and it's just very time consuming. So let's go ahead and do the optimization now. So I have all my inputs here, and you can see that when I double click on these, then I can give it a range here. And I have, see this is a very wide range here, 10 millimeters to 9999 millimeters. It's very difficult for it to find an answer with such a wide range because I have so many variables here. But let's go ahead and run this just to see what it does. So you can see that the first trial, the first run that it did here, has a R squared of 0.637. Run number 11 had a slightly better answer. And you can see that as we continue our runs, it has iterations up here. That's the number of runs that it's done. It is improving as we go. Hopefully this doesn't take too long. Are there any questions while this is running? Let's see here. Looks like there aren't. Okay, well, while that's running, I'm going to talk to you about what happened after I did this yesterday. So let me go to the other version of this model, which is here, and run the model and look at the runoff comparison chart. Okay, so what you see here is there are 3 lines. The red line is the GoldSim output of the runoff from the AWBM model. The black dashed line is observed, and the green line is from HEC-HMS. So you can see we don't have a great, it's not a great turnout here. I mean, it's okay. Some of these smaller peaks are working okay. This peak here matches well. The others do not match as well. You can see that on the tails here, as the flows drop off, that we match. It's okay. It could be better. So, and I worked on this for, I don't know, maybe a half hour or so, an hour yesterday. I could probably get this a bit better, but I did this all manually. I just made adjustments manually because the optimization wasn't quite getting me there, so I found I could get a little bit better by just understanding what the model's doing and making adjustments. Somebody is asking me a question, how's the average of measured flows computed in the R2? Okay, so let me show you. It looks like that model also finished, so it did. Okay, so the optimization is complete. And when you close an optimization, you get some options. And let me show you what those are. So you can see here, we finished with trial 334 with an R-squared of 0.86667. So it's okay, sort of decent, but let's see what that looks like. When I hit close, you'll see I have these options down here. Copy the optimized values into the element definitions. Yes, that's what I want to do. You could also copy them into the initial values of the next optimization run that you do. I'm not going to check that, but you could, and that would just make it so the next optimization run you do, it would just optimize starting with this best result here. Okay, so what I did by checking that box is it made it so these inputs, like BFI, for example, have this number here that came from the optimization run. But you can see we're in result mode, so I need to do a regular run now. So I'll go ahead and do that. And now we'll go up and we'll look at, interesting, this HEC-HMS tooltip is appearing from the HEC-HMS model. Anyway, what you see here is that we have a fairly decent fit on the peaks. You can see that the peaks are coming up here. Let me zoom in just a bit so you can see. I'm holding down the control key and drawing a rectangle here. So here are the peaks. You can see they're actually a little bit better than my manual calibration that I tried to do, but still not perfect. So that's what the calibration looks like. So somebody asked about the calibration. Let me show you. So essentially, I'm just doing this the R-squared equation here. The average daily from a simulation. So that would be Q here. That's this Q average right here. So to calculate that average, I'm running this model for a year. So I just take the Q gauge and I divide it by a year. So that's how I'm calculating it. Somebody said also, I never use more than 3 variables to optimize. Did you guys change the optimization algorithm that now we can have more variables without taking long to optimize? Well, no, we didn't change anything there, and it's probably just the nature of this particular model. It's probably simple enough that it's not taking that long. Plus, I have, what are my time steps here? Well, they're 15-minute time steps, but I could have changed it to 1-hour time steps, and it could have gone a little bit faster. I guess it just depends on the model, but no, we haven't changed anything with optimization there. And maybe it could also be with the ranges that I put in. Maybe my ranges are smaller. I'm not sure. Okay, so the conclusion from this is that the optimization did did an okay job, but we may want to do a further. So you look at the look at the beginning of this time series, how it's flatlined here. Well, this is probably due to the initial conditions of the soil. So let's go look at that. In the AWBM model, if I come in here to the calculations, you'll see there's this element here called surface stores. That's essentially these C1, C2, C3 surface stores here. And you can see a plot of it right here, overflows. This is what's happening. So the C1, the big one, that's the red here. And it currently has quite a large capacity, and it takes quite a bit for those to overflow. In fact, I don't think this is overflowing at all here. So the C3 in this case is not actually contributing to discharge from the, let me just check that. Let me look at the table, Q3. So Q3 would be the overflow from the third surface store. And it looks like there were a couple. Here's one right here. So it's okay. I guess it's just the line is underneath, and it's underneath the green and the blue. So let's change the thickness of the red. So I'm going in here to the properties, and I'm going to change this one here to be a little bit bolder, but also dashed so that you can see the others. Well, that is not what I expected. Let me go a bit larger here. Okay, well, they must be very small numbers. Yeah, this is millimeters per day. This is peaking at 800. If I look at the table again, yeah, these values are quite small. So anyway, what I'm trying to say here is that because the capacity of the third store is so large, we never hit. We're putting we're putting precipitation into it, but it never hits the capacity, therefore never overflows. Therefore, it does not contribute to the runoff in this optimized model case. So we may want to consider revising that, even though the optimization brought us to that point. Somebody said I was looking at Q3. I was looking at Q3. Should I not have been? I think oh, you're right. I'm looking at, interesting. I just assumed that the largest one was the third. Thank you for pointing that out. So it turns out that the optimization gave us a largest store for C1. So you're right. Thank you for pointing that out. So it's actually the green line. So it's the first surface store that we made the largest. Well, the optimization did that to us. I'm not sure I like that, and I would highly consider revising this after the optimization. And that's actually why I wanted to point to the manual calibration that I was doing. So let me go to that model. I hope I'm not confusing you too much here with all of these screens. But now we're looking at the model, same one, where I did a manual calibration. So in here what I did is I said, well, I know when I look at this plot here, I know that I need my base flows to be stronger than what the optimization produced. And what I mean by that is with these tails down here, what we were getting in the other model is the tail was dropping down too quickly to 0. And I needed it to trail off slowly like it's doing here with the black dashed line. And so I knew that my base flow store needed to have a higher flow and more attenuation. So I adjusted these factors manually here. I also made my surface stores increase as we walk down from C1 to C3. So I have a small surface store here for C1, and it gets increasingly larger as I walk down to C3. So when we run this model, oh, it's already run, we look at the overflows, and you see here that S1 is the smallest, S2, and then S3, like that. And somebody said you could check the ranges for the C1 variable. If you're saying I could check the variability by looking at the range in the sensitivity analysis, maybe I'm not sure exactly what you're saying by checking the ranges, or maybe what the literature says about this type of model. Yeah, I could check those things. That's definitely true. So what I did, though, when I was manually adjusting these numbers, I actually did play with these quite a bit, these three numbers, the depths of C1, C2, and C3. And then I played with the recession constants. And that is how I got to this chart here. So you can see that I still probably need to do a bit more work on the peak here. But you can see that from the very beginning, it's, it's decent, I guess. So that's where we're at now with that one. Okay, so I want to talk to you about a couple more things with the AWBM model. You can see that the calibration it's going okay. Probably need to spend some more time with it, but that gives you an idea anyway of how it compares to a third-party model, HEC-HMS, and also the comparison to the observed flows, and how this type of model, the AWBM model, though quite simple, still is a fairly robust and flexible model that could be used in a real-world situation. Okay, so with that, I'm going to yet another version of this model. This one. Okay, so this is exactly the same thing again, but it's the model that you would see if you download from our website. It has this model validation container here. What that is results from yet another tool. It's called the rainfall-runoff library. You can read about it here. If you go into the container, you can read all about it. But essentially, I just use it to validate the results of the GoldSim model. And whoops, I need to first remove my inserted time steps, because that was the whole point of this exercise, was to show you the difference. So let me do a regular run. This is what you'll see when you download our model from our library. You'll see that the red line, which is GoldSim, matches with the black line of the RRL2 toolkit. Okay, so we have validation there. Now what I want to do is I want to show you the effect of inserted time steps in the model. In fact, I should probably do another run just to make sure. Okay, there are a couple of things you need to know about with inserted time steps in GoldSim. So GoldSim is different. It's different than a lot of tools that you're probably used to that do continuous simulation, in that GoldSim allows inserted time steps. And the reason it does is because GoldSim is used for looking at risk and reliability of events that could occur. And events occur randomly in the real world. And so GoldSim does allow inserted events. And this comes as a surprise to many people that are coming from maybe a more hydrology background, where a lot of tools do not do that at all. Well, in GoldSim, you can have inserted time steps, and that can cause havoc on traditional hydrologic models like AWBM, for example. So I want to talk about that a bit, because it will come as a surprise to you if you're coming from that world. So in GoldSim, if you go to the simulation settings, what you'll see here is at the bottom there's an advanced button. In this model, I have a basic step of 1 day. That does not necessarily mean that all calculations are always done at midnight on each day. It doesn't. It depends. First of all, it depends on what you've set in your advanced settings here. So if I click on that, you'll see here there's a checkbox, allow unscheduled updates, recommended. There are various reasons why this is recommended, but just note that it is checked, and so GoldSim can insert unscheduled events. Now, when does GoldSim do that? Well, there are different ways that it does it. The most common for those that are doing water management type models would be in reservoirs with bounds. If you have one or more reservoirs in your model that has upper and lower bounds, or lower bounds set, then you most likely will have some inserted time steps in your model, and you may not realize it. Okay, so you can find out if you do by simply checking this box down here, include unscheduled updates, and it will show you when you might be having inserted time steps. So I just ran the model, and if I go here to table, you see here in the date column that I have some dates with random looking timestamps on them. Well, that's an inserted event right there. And how did that happen? Well, it turns out that there is a reservoir in this model, and it has a bound on it. So let me show you that reservoir. If I go into the calculations, you'll see that there's this reservoir element here. Now, I realize this might be confusing to existing GoldSim users out there because these icons look different. This is the reservoir element, which if I go to the version that you're used to, you'll see, oh, well, I don't have one on this view. Do I have another model open? Just real quick here. So this is the current version of GoldSim. All right, reservoir element. So there's the old reservoir element. This is the new reservoir element. Anyway, in the reservoir element, there is lower bound, upper bound set. This is our surface stores right here. And it turns out that as we were looking at, you see that our surface stores have a capacity, and we're hitting that bound. Every time we hit that bound, it inserts a time step. Every time we hit the lower bound, when we come down, for example, down here, we hit it. We insert a time step exactly at this moment that it hits the lower bound. Okay, something to be aware of, especially when you're working with a tool that maybe was not intended to be working with inserted steps. So what do? Well, what we need to do is, in this case, if we want to have exact answers, actually, when I say exact, let me go back to the validation. And you probably will find a couple of points in here that are not exact. Here's one, right here. So we have inserted a time step right here. The RRL toolkit did not do any update at this exact time. So this is a bogus point right here. It just copied from what it was earlier. So you can ignore that point. But GoldSim inserted this point right here. And because each updated value is partially a function of what it was previously, it changes the next value. So that's why this point is now off slightly, because it's a function of what happened right here, if that makes sense. So it's almost like just having smaller time steps, more calculations. That means you get a slightly different answer. So that's what's happening. Okay, so what do we do? Well, in this case, what we could do is we could disable the inserting of time steps. So let me show you the answer when we do that. So I come up here to the simulation settings, I go to advanced, and I uncheck allow unscheduled updates. So now it will not include any unscheduled updates. When we do the run, I look at the validation plot, go back to the same exact point, and you see we get exactly the answers that the other tool got. Okay, I hope that makes sense. If you have any questions, please let me know. But inserted steps, it's important that you're aware of what they're doing. Okay, so while disallowing the inserted steps is useful for this case, it may not be useful for your main model, your water balance model. You may actually need them in your main model. So what do? Well, what I would suggest is that you isolate portions of your model that need inserted events. So think about the parts of your model that need that and put those into their own container. So what I'm going to do is, first of all, let's pretend like this timed event generator is your other part of the model, right? That's generating all of these inserted events. Let's say there's a whole bunch of reservoirs in there. They're hitting bounds and they're inserting all these events. The effect that would have is essentially like saying there's random events occurring in your model. So I'm setting this to random time intervals, which means that approximately once a day something happens, but it's an average, right? So the random, based on a Poisson distribution, it will say sometimes it'll insert event every 3.5 hours and every 3 days, and anyway, it's random. So we're generating random events. Okay, now we run the model. Oh, sorry, I need to go back to the simulation settings and allow unscheduled events. Okay, so now I run this model and I go look at the validation, and you can see again, once again, we're in that same situation. We've got a bunch of inserted events and we're off a little bit. Okay, so what can we do? Well, let's isolate the part of your model that is inserting the events and isolate it from our hydrologic functionality. So I create a new container, okay, and then I put this, I'll pretend this is a whole model here, right? I put that in here. And now what I'm going to do is I'm going to the properties of this container and I'm going to say it has its own clock. Then I go to the internal clock and I say, what's the maximum time step? And I'm going to say, let's just say 0 days. Okay, so now we have isolated inserted events in here from the rest of this model over here. And let's see, I'm trying to think here. There's still going to be inserted events at this surface store here, but the effect of all of those events are not going to be affecting the model. So if I come back in here and we see what we were looking at earlier, and you can see that we're not having any of that effect anymore from the inserted events. Okay. All right, so let's see, I think that's all I wanted to say about the inserted events. If you have any more questions, please feel free to let us know. You can ask me at the end of this webinar. I just wanted to show you the HSPF model now. So let's go to that one. This model is, I did this in the current version, so it'll probably look more familiar to you. But this model has a lot more input parameters than the AWBM model. You can see I have 15 here. So this one is really important to do a sensitivity analysis before you try to do any kind of optimization, because this is just a ton of inputs here. So I put all of these in there and I did a run, and the tornado chart looks like this. So you can see here that we could probably strip out some of these inputs that are kind of down on the lower end down here, but kind of focus more on these upper variables right there. So that's kind of what I did. And this run, when I run this one, and I need to check on that error that I got there. And you can see here that I still have issues with the base flows. So there are a lot of inputs in this model, like I said, and I'd have to go look at them, but I'm pretty sure that I've got issues here with the groundwater outflows. And what I mean by that is, if I go back up here to the inputs, again, this model can be downloaded from our website, but you go in here to inputs, and then catchment definitions. Here are all the definitions, so quite a few. But what I'm thinking is that I have the groundwater parameters. So groundwater recession coefficient, that would probably be a good one to start with. Let me see what I did. The recession. Okay. Anyway, so some of these might need to be adjusted here. Maybe some of the infiltration numbers as well. So, then again, this model, it has 2 versions on our website. One is this current version, which represents a single catchment. So the calculations are done as scalar calculations. But on our website, if we go up here, let's see, do a search for HSPF. So HSPF, this is the one that I'm using right now. But there's also, okay, this doesn't show up in the search, so let me just browse for it. So if you go to GoldSim Model Library, then Applications, then Hydrology, there is in here somewhere a vector version of HSPF. Here it is, vector HSPF in GoldSim. So this is the same thing, but it's the calculations have been vectorized. So that would be useful for when you want to represent multiple catchments. But I would be interested to know if any of you have a more successful calibration than I did. And I didn't spend a whole lot of time with this. I just did a couple of optimization runs and ended up with that. So the peaks are okay, but it's definitely on my interflow and groundwater outflow that I have problems here, as you can see. So I'll probably take a little bit more adjustments on those, probably manually, to get a better fit there. So anyway, that's the HSPF model, and you can see here that there's quite a bit more to it. For example, here's the flow network from that schematic I was showing you. Rainfall comes in and it gets intercepted in various ways, and then it's just simply split to the different zones. You end up with the upper surface flows, and then the soil flows down here. Lower zone, active groundwater. Inactive groundwater is essentially lost water. But those are all functions of these other calculations going on: infiltration, overland, interflow, etc. And that concludes the webinar on the HSPF and AWBM models. I hope this was useful for you, and thank you very much for taking the time to join us.